Welcome to today's paper reading. Today's paper is titled OmniSSR, Zero-Shot Omnidirectional Image Super Resolution Using Stable Diffusion Model. This paper was published on AR14 by Runyi and colleagues from Peking University. The abstract introduces the concept of omnidirectional imaging, ODIs, and how high-resolution ODIs can enhance various visual tasks. Most current super-resolution methods for ODIs employ end-to-end learning strategies, which often result in less realistic images and limited generalization capabilities. The abstract then shifts focus to diffusion models, which provide strong priors for visual tasks and have been effectively applied to image restoration tasks. Specifically, the Stable Diffusion (SD) model is leveraged to achieve omnidirectional image super-resolution with both fidelity and realness, termed as OmniSSR. The method involves transforming equirectangular projection (ERP) images into tangent projection (TP) images, using SD for iterative sampling, and applying the octadecaplex tangent information interaction (OTI) and gradient decomposition (GD) techniques to ensure better consistency. The OmniSSR method is zero-shot, meaning it requires no training or fine-tuning, and its effectiveness is demonstrated through experiments on two benchmark datasets. Omnidirectional images, ODIs, are unique in their ability to capture the entire scene in all directions, surpassing the limitations of planar images with a narrow field of view. Super-resolution (SR) techniques are employed to enhance the visual quality of these ODIs by increasing their resolution, thereby revealing finer details and enabling more accurate scene analysis. This is particularly crucial in applications such as virtual reality and surveillance, where high-resolution ODIs are essential for precise perception and decision-making. However, current ODIs methods face several challenges, including producing deterministic outputs that prioritize data fidelity over visual perception quality, requiring high data demands, and issues with global continuity when processing tangent projection images. These challenges highlight the need for innovative approaches to effectively address ODIs. Figure 1 presents a comparison of the zero-shot omnidirectional image super-resolution (ODIs) achieved by OmniSSR and the current state-of-the-art method, OSRT. The figure highlights that OmniSSR maintains both fidelity and visual realness, producing images with vivid and realistic details. In contrast, OSRT results are shown to be over-smoothed and distorted. The visual comparison in parts A and B of the figure demonstrates the superior performance of OmniSSR in preserving fine details and ensuring a realistic visual output. Zooming in on the images provides a closer look at the enhanced details and the overall quality of the super-resolved images. The current state of image super-resolution methods based on deep learning can be categorized into two main approaches. The first involves end-to-end network training methods, which use image pairs consisting of low-resolution degraded images and high-resolution ground truth images for training. These methods employ network architectures such as CNNs and transformers. The second category utilizes generative models as priors, such as Jians and diffusion models, where low-resolution images are used as conditions to generate high-resolution images. Specifically, in single-image super-resolution using Jian priors, pre-trained Jian networks transform image features into latent space, searching for the corresponding latent code to reconstruct high-resolution images. The method section of the paper begins with the ERP left-right arrow TP transformation, which involves determining the positions of target image pixels within the source image using mnemonic projection. This transformation allows for the creation of forward and inverse mapping functions between ERP and TP images. The section then moves on to iterative denoising for super-resolution, where image priors are used to enhance the resolution of planar images through a time-aware adapter and denoising unit. Finally, the OmniSSR pipeline is outlined, detailing the pre-processing steps, projection onto tangent planes, and the use of gradient decomposition correction to ensure consistency in the super-resolution results. Figure 2 provides detailed insights into the mnemonic transformations used in the OmniSSR method. Part A illustrates the conversion process from equirectangular projection, ERP, to tangent projection, TP, which is crucial for transforming omnidirectional images into a format suitable for super-resolution processing. Part B highlights the pre-upsampling strategy proposed in the octadecaplex tangent information interaction (OTI) section, which effectively mitigates the information loss that typically occurs during these transformations. This pre-upsampling approach ensures that the intermediate images retain sufficient detail, thereby enhancing the overall quality of the super-resolved output. Figure 3 provides an overview of our proposed OmniSSR pipeline. The process begins with a low-resolution omnidirectional image in ERP format, which is projected onto tangent projection (TP) images. These TP images are then iteratively refined using Stable Diffusion (SD), with a time-aware adapter and a controllable feature wrapping (CFW) module. During each step of diffusion sampling, the gradient decomposition (GD) correction technique is employed to ensure consistency constraints for the intermediate results. After T steps of sampling, the final result E0 is obtained, characterized by high resolution and improved visual quality. For the experimental evaluation of OmniSSR, the authors utilized the ODIs dataset with 97 images and the Sun 360 panorama dataset with 100 images. The ground truth images were of size 1024 by 2048 pixels. Pre-trained models from Stable SR were adopted, which included a SR network based on SD, featuring a time-aware adapter and a controllable feature wrapping module. The experimental settings involved setting diffusion sampling steps to 200, using bicubic downsampling for degradation, and setting specific hyperparameters for GED correction. Figure 4 presents a visualized comparison of x2 and x4 super-resolution (SR) results on the Sun 360 test set. The images 001 and 009 are identified by their ID numbers and the test set file names. For each SR result and the downsampled image, the peak signal-to-noise ratio (PSNR) and structural similarity index measure (SSIM) are calculated against the high-resolution (HR) ground truth. The visual results indicate that OmniSSR demonstrates superior capability for detail recovery compared to other methods, particularly evident in textual elements, complex objects, and small-scale objects. This superior performance is further supported by the quantitative metrics, showing OmniSSR's ability to recover highly detailed and realistic visual effects from the test images. Figure 5 presents a visualized comparison of super-resolution (SR) results at x2 and x4 scales on the ODIs test set. The images with ID numbers 067 and 049 are used for this comparison. Additionally, the peak signal-to-noise ratio (PSNR) and structural similarity index measure (SSIM) are calculated between the ground truth and each SR result, as well as the downsampled image. This analysis helps in evaluating the effectiveness of different SR methods by quantifying the quality of the reconstructed images. Figure 6 presents an ablation study on the choices of gamma-P, gamma-E, and gamma-L parameters in the context of OmniSSR performance. The study uses WSPSNR and PIPS as evaluation metrics to assess fidelity and visual quality under various gamma settings. The results are illustrated in three scenarios: A. Fixing gamma-P and gamma-E while adjusting gamma-L, B. Fixing gamma-E and gamma-L while adjusting gamma-P, and C. Fixing gamma-P and gamma-L while adjusting gamma-E. The study reveals that OmniSSR achieves the best performance when gamma-P is set to 1, gamma-E to 1, and gamma-L to 0.5. Table 1 presents the super-resolution (SR) results under bicubic downsampling on the ODIs and Sun 360 panorama datasets. The table compares various methods including bicubic, DDRM, DPS, GDP, PSLD, DIFF-IR, Stable SR, and OmniSSR across different scales, x2 and x4. Metrics used for evaluation include WSPSNR, higher is better, WSSIM, higher is better, FID, lower is better, and PIPS, lower is better. The best results are highlighted in red, and the second best results are highlighted in blue. OmniSSR demonstrates superior performance in terms of both fidelity and realness metrics, outperforming existing diffusion-based methods for ODIs tasks on different scales. Table 2 presents a detailed comparison of the performance of x4 super-resolution (SR) tasks using supervised methods trained on the ODIs dataset. The methods evaluated include SwinIR, OSRT, and OmniSSR. The table provides metrics such as WSPSNR, WSSIM, FID, LPIPS, NIC, and DISTS to assess the quality of the SR results. The best results across these metrics are highlighted in bold, allowing for a clear visual comparison of the effectiveness of each method. This comparison is crucial for understanding the strengths and weaknesses of each approach in the context of times for SR tasks. Table 3 presents the ablation studies of OmniSSR focusing on the impact of different input types, ERP, TP, the presence of OTI, and GD correction on the performance metrics of the ODIs dataset. The best results are highlighted in bold. The study evaluates the effects of these factors on WSPSNR, WSSIM, FID, and LPIPS, providing insights into the optimal configurations for OmniSSR. Notably, the presence of GD correction, especially when applied in post-process, significantly improves the performance metrics. Table 4 presents the results of the pre-up sampling strategy applied at different scales. The notation, X, Y, indicates bicubic-based upsampling at X times scale to ERP before ERP-TP transformation, and Y times scale to TP before TP-ERP transformation. The best results are highlighted in bold, showcasing the effectiveness of the strategy in mitigating information loss during the transformations between ERP and TP images. Despite achieving competitive performance and better visual results in ODIs, the study identifies several limitations. Firstly, the inference of the diffusion model is time-consuming, taking approximately 14 minutes per ERP-formatted omnidirectional image to be super-resolved into a size of 1024 by 2048, which poses a challenge for real-time super-resolution. Secondly, the pipeline requires multiple conversions between ERP and TP, which, while improving performance, consumes additional inference time. Lastly, there is a need for further exploration of the convex optimization properties of GD correction, including designing gradient term coefficients that are adaptive to reconstruction results and degradation types. The OmniSSR method leverages the image prior of Stable Diffusion, SD, to achieve zero-shot omnidirectional image super-resolution. The octadecaplex tangent information interaction, OTI, is employed to enhance the super-resolution process, improving the fidelity and realness of the restored images. Additionally, gradient decomposition, GD correction, based on convex optimization algorithms, refines the initial super-resolution results, further enhancing the quality of the images and mitigating overfitting issues. Thank you for watching.